Alright, welcome everyone. The second video, starting to talk about acids and bases. So in the first video, we defined what an acid and base is, right? Our Barnstead-Lowry definition that we'll focus on mainly here is, right, proton donor is an acid, proton acceptor is a base, right? So here, I have two different acid kind of base type reactions, right? So look in this first reaction, try to identify what is our acid, what is our base, and such, right? Look at this reaction, we have HNO2 plus H2O forming NO2 minus plus H3O plus, right? So we see here, right, that the hydrogen is being transferred in that direction, right? Comparing kind of your reactants and products, right? See, that's where the hydrogen went, it left the NO2 minus and went to the H2O, okay? So that means this is our acid, and this is our base, okay? Right, but notice here that in this reaction I decided to write kind of this equilibrium error, right? Implying that the reaction go in the reverse direction, okay? So, right, if I think of this reaction going in the reverse direction, in this case, right, if these are now my reactants, right, if I think of my reactants now here on the right, okay, the hydrogen is being transferred from H3O plus to NO2 minus, okay? So what I would call this, I wouldn't call this just an acid, what I'm going to call this H3O plus, I'm going to call this a conjugate acid, and I'm going to call my NO2 minus, which acts as a base, my conjugate base, okay? And why I'm calling them conjugate acids and conjugate bases is because every acid has a conjugate base pair, okay? So, and every base has a conjugate acid pair. So every acid, once it donates that proton, it starts acting like a base, right? So HNO2, it donates a proton, forms NO2 minus. That NO2 minus is now a base, and that will act as a base in any type of acid-base chemistry, okay? And so this acid, right, my acid here, HNO2, forms a conjugate base, NO2 minus, right? To go from the acid to the conjugate base, okay, typically you're just removing an H plus, right? So here I see if I take the H plus away from NO2, I form NO2 minus, that's its conjugate base, right? And then I have, right, my base here, water, that forms the conjugate acid H3O plus, right? And so, right, and so we have our acid has a conjugate base, and our base has a conjugate acid. And these are, again, are called conjugate acid-base pairs, okay? So we next look at the second reaction here. Again, now we're looking at, okay, where did the proton get transferred? And I'm looking at this reaction and say, oh, okay, if I compare the reactants and products, I see NH4 or NH3 gained a proton, right? It became NH4 plus, right? And then H2O lost a proton, so then it became OH minus, right? So in this reaction, this is my acid, and this is my base, right? And so, again, my base has a conjugate acid that it forms, and the acid forms a conjugate base, right? So again, I have my conjugate acid-base pairs, right? My acid here forms its conjugate base, and my base forms its conjugate acid, right? And again, these are acid-base pairs, okay? And every acid has a conjugate base, every base has a conjugate acid, right? There's always these pairs, right? Because again, once you've removed a proton or added a proton to a molecule, it becomes, you know, it switches from being an acid or a base, okay? And we'll note here, I picked these two reactions also to show and emphasize the fact that H2O here can act as an acid and a base, okay? So water can be an acid, and I'll say and base, okay? Now, it's not going to be an acid and base potentially in every reaction together, things like that, but right, in any given reaction, water can act as an acid, or it could act as a base. Okay, not many other compounds out there that do that. There are some other ones, polyprotic acids and things like that we'll talk about later. Okay, but water is one of these compounds that can act as either an acid or a base. Okay, so right, again, every acid-base reaction, right, will have an acid with its conjugate base and a base with its conjugate acid, right? So every acid-base reaction, right, you can think of as an equilibrium reaction where there's an acid and a base on both sides of the reaction, okay? Right, and that equilibrium reaction is going to favor transferring the proton from the stronger acid to the stronger base, okay? Right. And so knowing your strengths of acids and bases can tell you kind of what direction that equilibrium reaction is favoring, whether it's favoring products or reactants, okay? And we'll note here, because this will pop up a lot, okay, that here I have this list of acids and their conjugate bases, okay? Or you can think of bases as and their conjugate acids, however you want to view it, right? Okay. So we have things that are very strong acids like HCl, H2SO4, HNO3, right? Our acidic strength is increasing on the left side, okay? Note here that the strength of the conjugate base is increasing as I go down, right? While the acid increases as I go up, okay? And that's because there's this like inverse relationship between the strength of an acid and its conjugate base. So a very strong acid is a very weak conjugate base, right? Essentially negligible, right? I mean, saying like, these don't really act as a base, right? And you can think about this, right? An acid really wants to give up its proton, right? A strong acid means, hey, I don't want this proton, get it out of here, right? HCl is like, the chlorine is saying, get this proton away from me, get rid of this H plus ion, don't want it, don't need it, don't care, right? Well, if it really wants to give up that H plus ion, right, then now its conjugate base, the Cl minus ion, right, it doesn't want to take it back, right? It's not going to want back that hydrogen ion, right? It's not going to want to take back H plus to form HCl, okay? So it's really not going to act as a base because it wanted to get rid of that H plus ion and it's not going to ever want it back, right? So the stronger an acid is, right, that the more it wants to give up H plus, so the weaker its conjugate base is going to be, because if it wanted to give away that hydrogen ion, why in the heck would it ever want it back, right? And so, right, and then when you get into the realm of having weak acids, which we'll talk plenty about these, like HF is a weak acid, okay? Its conjugate base, F minus, is also a weak base, right? So HF can act as an acid, and F minus will act as a base, okay? While again, Cl minus is not going to act as a base whatsoever, okay? Because it comes from a strong acid, right? It's conjugate base of a strong acid, so it's never going to really act as a base, right? Similarly, right, things like CH4, right? CH4 is never going to give up its proton. It doesn't want to give up that proton to form CH3 minus, right? But CH3 minus really wants a proton, okay? Right, so your strong bases, okay, are things that really, really, really want protons, right? If they really, really want protons, they're not going to want to give them up, right? So your strong bases, right, are going to form negligible acids, okay? So again, there's this inverse relationship between the strength of the acid and the strength of the conjugate base, right? Stronger the acid, weaker the base, stronger the base, weaker the acid, okay? Between your acid-base pairs, your conjugate acid-base pairs, okay? Right, and so I talked about as well how water can act as an acid and base, and there's actually a reaction where it does both, and that's the autoionization of water reaction, where water reacts with another water to form OH minus and H3O plus, okay? This, right, and this is an equilibrium reaction, okay? This reaction occurs in every solution of water, because every solution of water has a bunch of water to be able to react with itself. So this reaction occurs in every solution of water, okay? Now this reaction favors the reactants, okay, but it does occur, okay, and this is an equilibrium reaction. So what that means is in every single solution, right? Every single solution where water is your solvent, you have this equilibrium reaction, okay, which has an equilibrium constant that we call Kw. So the W here is just indicating that it's for this reaction, right? That's for the reaction of the autoionization of water, right? So this Kw equilibrium reaction, right, has an equilibrium constant of just concentration of H plus OH minus, or again, you could write this as H3O plus OH minus, right? These two reactions here, right, are indicating the same reaction, okay? One, you're just using the H3O plus form, the other using just H plus, right? So again, they're like the same reaction, same thing we're talking about here, just different names, okay? But, and so this Kw, okay, this equilibrium constant related with the autoionization of water is equal to 1.0 times 10 to the minus 14 at 25 degrees Celsius, okay? Right? And so what does this mean? Well, what it means, right, is in any solution where, again, water is your solvent, you always have this equilibrium established, right, between H plus ions and OH minus ions, right? That always the concentration of H plus times concentration of OH minus has to equal Kw, okay? Always, always, always in any solution, right, where water is the solvent, okay? Now in just pure water, neutral solution, right, those concentrations are equal, H plus and OH minus are equal, okay? But again, the product of those two things will equal 1 times 10 to the minus 14, right? Well, in an acidic solution, okay, we'll talk more about acidic solutions versus basic and things like that. But in an acidic solution, you have a lot more H plus ions, okay, than you do OH minus. But that product of H plus and OH minus still always equals 1 times 10 to the minus 14. In basic solutions, you have a lot more OH minus concentration than you do H plus. But again, the product still equals 1.0 times 10 to the minus 14. So again, and so what's the usefulness of this? Well, this product here, right, this always gives you a relationship to be able to convert, right, between H plus and OH minus, okay? So any solution of water, if I know the concentration of OH minus, I know what the concentration of H plus is. I just got to use this equation here, right, to convert between the two things, okay? But I can use this autoionization equilibrium constant for water to convert between the concentration of H plus and OH minus in any solution of water, okay? Right? No matter what you add into that water, concentration of H plus and OH minus always have to multiply together to get 1 times 10 to the minus 14. So I can always use that relationship to convert between the concentrations of H plus and OH minus.